Today in AC electrical circuits, we're going to be looking at lab number 2, vector and AC waveform review. Most of these topics have been covered in math. Under objective, it says the proper manipulation and representation of vectors is paramount for AC circuit analysis. Addition, subtraction, multiplication, and division of vectors in both rectangular and polar forms are examined in both algebraic and graphical forms. Representations of waveforms using both phasor and time domain graphs are also examined. The voltage and current relationship in an AC circuit are based on the right angle triangles. I have a note here that I in electronics is used for current, so we're going to be using J for our imaginary numbers instead. I is still used on your calculator. Now to perform these calculations, you need to put your calculator into complex mode, and your calculator requires the following 4 buttons. So somewhere on your calculator you should see an I button, something that looks like an angle button, an arrow pointing to R, theta, and an arrow pointing to X, Y. So this is my calculator. It's a Sharp EL520W Advanced DAL calculator. It's about $20. And I just wanted to show you the buttons on my calculator. You can see underneath the A, B/C key there's a small I here. And under my DMS key you can see there's a small angle. Above my 8 key, you can see I have the arrow, and it puts it into polar coordinates. And you can see another arrow here that puts it into rectangular coordinates. The reference sections are from Sean's Outlines, Basic Electricity 2nd edition. Chapter 17 talks about complex numbers on the first 7 pages. And Chapter 12 talks about the principles of alternating current, and we're looking at the first 9 pages. So this is Chapter 17 from your textbook, where they talk about complex numbers. And it starts out with a definition of complex numbers. You can see here they're showing you the real part, which is x, and the imaginary part, which is jy. And they have a nice section on rectangular and polar forms of complex numbers. And they give you a nice graph of what a complex number looks like, similar to the one that I put on the front of your lab page. They give you the conversion formulas to go from polar to rectangular and rectangular to polar. And they cover operations with complex numbers, giving you examples of an addition here. And they show you what it looks like graphically to solve some of these equations. And finally finishing up with division of complex numbers, both in rectangular and polar form. Chapter 12 talks about the principles of alternating current, and they start with generating an alternating voltage, and they cover the frequency and the period. Here they're getting into characteristic values of voltage and current. So you can see under theory overview we're going to be talking about the right triangle, and basically we have an x-axis and a y-axis, so this is a basic two-dimensional graph. The x-axis is called the real axis, and it's either the current, voltage, or resistance of the resistor. So we always draw that on the horizontal axis. On the vertical axis, labeled y, is going to be your complex component or your imaginary part of your waveform. So if it's an inductor, it's going to be plus 90 degrees. If it's a capacitor, it's minus 90 degrees. You can see we have the x, the real part, the y, the imaginary part, and we have the z, which is the resultant, and in AC circuit, Z stands for impedance or AC resistance. It's the resultant of X and Y. So you can see in the rectangular form, the formula is X plus Y J, and we're using J instead of I so that we don't confuse it with the current. So converting to the polar form, we've got X and Y. We want to find out what Z is, and I think we all recognize Pythagorean's theorem, and that stated that Z squared is equal to X squared plus Y squared, so Z is equal to the square root of X squared plus Y squared. And the angle that Z makes to the x-axis is arctan of y over x, so y being the opposite and x being the adjacent. Just to jog your memory, j or I is defined as the square root of -1. To convert from the polar form, where we have a magnitude and a phase angle, converting to rectangular form, x is equal to z cos theta, and y is equal to z sine theta. So looking at operations with complex numbers, in the rectangular form, it's fairly easy to add two complex numbers together. We add the two real components together, and then we add the two imaginary components together. So in this case, 2 plus 3 is equal to 5, and 4 plus -1 is equal to 3. For subtraction, 2 minus 3 is equal to -1. And 4 minus -1, which becomes 4 plus 1, is equal to 5. Under operations with complex numbers in the polar form, when we do multiplication, all we do is we multiply the two magnitudes together and we add the two angles. When we do division, we divide the two magnitudes and subtract the two angles. So I've left a note here on the page that it's easier to add and subtract using rectangular form, multiply and divide in the polar form. So on the next page on theory overview for phasor and time domain graphs, we can see we have our standard sine wave, and our sine wave covers 360 degrees. So when we look at it from a circular motion, you can see a complete circle is 360 degrees. We reach our maximum at 90 degrees, and then at 180 degrees we go through the zero line, our negative maximum, and back to the zero line at 360 degrees. A max is the maximum of our waveform. In this case, they're using 1 as the maximum. The RMS value is not the same as the average value. The RMS value is equal to 0.707 times the maximum value. 0.707 happens to be 1 divided by root 2. The frequency is equal to 1 over the period, and the period is equal to 1 over the frequency. We also have to note that omega is equal to 2 pi f, and f is the frequency. So when we look at our waveform formula, we can see that A at time, now that would be at any point on this waveform, is equal to A max, which is this point, sine, this is a sine wave, omega at that same time. And omega is equal to 2 pi f. So under theory overview, I have a section here on shifting graphs up, down, left, and right. And this came from a website called onemathematicalcat.org. And they give you an example of shifting a waveform up by 2 divisions. So your formula becomes y equals f at x plus 2. So it moved it up 2. If we're shifting the waveform down by 2, y equals the function at x minus 2. So that shifts it down. Okay. Under here it says movements up and down change the y values of points. Transformations that affect the y values are intuitive, meaning that we're going to either add or subtract from it to shift the waveform up or down. Now when we're shifting the waveform to the left or shifting the waveform to the right, it says movements left and right change the x value of points. So transformations that affect the x values are counterintuitive. And what that means is y is equal to the function of x plus 2, or y equals the function at x minus 2. So when we want to shift to the right, we actually subtract 2 from our function. When we want to shift to the left, we actually add 2 to the function. So in this diagram, we're taking a look at leading by 90 degrees versus lagging by 90 degrees, and it all depends on which waveform you use as your reference. So if we take the dotted line waveform as our reference, we can see that the solid line waveform is lagging by 90 degrees. So we say it's minus 90. So the first waveform crosses the 0 line. The solid waveform crosses sometime later, so it's lagging. If we use the solid waveform as our reference waveform, then the dotted line waveform is actually leading by plus 90 degrees. So the solid waveform crosses the 0 line here. The dotted line waveform crosses the line back here. So it crosses the line first before the solid waveform. So in this diagram, we're looking at a waveform with a DC offset. So you can see our reference waveform is the thinner lined waveform. Our thicker line waveform is actually on a DC offset. Looking at our waveform expressions, usually we use a small letter V for voltage or a small letter I for current, depending on what the waveform is that we're looking at. On this side we have the Phasor form of the same example. So usually the Phasor form is a capital letter, usually with a bar on top of it, indicating that it is the Phasor form. So looking at our waveform expression, we can see it's of the form V equals A max sine theta, or A max sine omega t. Remember that omega is 2 pi f, and it could be plus or minus a phase angle. So looking at these time domain examples, we can see V equals 10 sine 2 pi 100t. In this case, 10 is the maximum value, so it'd be plus 10 volts minus 10 volts. The 100 represents the frequency, so this would be at 100 hertz. In the phasor form, we normally use the RMS value. So we take the 10 and divide it by root 2, or you can take the 10 and multiply it by 0.707. 0.707 equals 1 divided by root 2. On the second example I have here, I have a current I, and it's equal to 4 sine omega t minus 40 degrees. So the 4 is the maximum, so it would be plus 4 milliamps peak minus 4 milliamps at the negative peak. And you can see it has a phase shift, and it says of minus 40 degrees. That would be shifting right. When we shift right, we say minus as part of the function. And shifting right is actually lagging. When we write it in the phasor form, we have to convert the peak to RMS, so we do the 4 divided by root 2. And in this case, we actually have an angle of minus 40 degrees. You notice in the time domain, we can pick up the frequency from 100, that would be in hertz, or it would be part of the omega. Remember, omega is 2 pi f. When we look at these in the phasor form, you'll notice that there is no frequency. So question 1, under procedure, we're going to convert the following to rectangular form. So 4 at an angle of 15 degrees. X is equal to z cos theta, which is equal to 4 times the cosine of 15 degrees. That works out to 3.864. Y is equal to z sine theta, which is equal to 4 times the sine of 15 degrees. That works out to 1.035. So our formula becomes 3.86 plus 1.04j. So under procedure, step 2, we're going to convert 3 at an angle of 60 degrees. So x, which is the real component, is 3 cos 60, which is equal to 1.5. The imaginary part is equal to 3 sine of 60, which is 2.598. So our formula becomes 1.5 plus 2.6j. So under procedure, step number 4, we're going to convert the following to polar form. So we're going to take 4 plus 3j. So z is equal to the square root of x squared plus y squared, which is equal to the square root of 4 squared plus 3 squared, and that equals 5. Theta is equal to the arctan, and on your calculator it's probably going to be labeled tan to the minus 1 of y divided by x, which is equal to arctan of 3 divided by 4, and that works out to 36.87 degrees. So the answer is 5 at an angle of 36.9 degrees. Under procedure, step number 5, we're going to convert 283 minus 1,140j. So z is equal to the square root of 283 squared plus 1,140 squared, and that's equal to 1,175. Theta is equal to arctan of minus 1,140 divided by 283, and that's equal to minus 76.058 degrees. And this is one of the calculations that we're going to be doing in one of the labs coming up. So under procedure, step number 6, we're going to perform the following operations. So we're going to add 10 plus 8j to 2 minus 4j. So remember, we take the two real components and add them together, and then we take the two imaginary components and add them together. So 10 plus 2 is equal to 12, and 8 minus 4 is equal to 4j. So under procedure, step number 7, we're going to subtract 6 minus 2j from 2 plus 10j. Remember, we take the real components first, so the 2 minus 6 is equal to minus 4, plus the 10 minus the minus 2j. So that becomes plus 10 plus 2j, which works out to 12j. So under procedure, step number 8, we're going to take 1,590 at an angle of minus 90 degrees and divide it by 1,880 at an angle of minus 58 degrees. And this is going to be one of those calculations coming up in a future lab. So what we do is we take the 1,590 and divide it by the 1,880, and that works out to 0.85 or 850 milli of whatever we were working with. And for the angles, we just subtract them, so it becomes minus 90 minus minus or plus 58, and that works out to minus 32 degrees. And under procedure, step number 9, we're going to take 6 at an angle of 90 degrees times 3 at an angle of minus 44 degrees. In this case, we take the 6 times 3, which is 18, and then for the angle, we take the 90 plus minus 44 degrees, and that works out to 46 degrees. So under procedure, step number 10, we're going to perform the following non-right angle operation. So we're going to add two phasors together. So it's 4 at an angle of 15 degrees plus 3 at an angle of 60 degrees. And the hint is to convert it to rectangular form to perform the add. And we've already done this in step number 1 and 2. So in step number 1, we converted 4 at an angle of 15 degrees to 3.86 plus 1.04j. And in procedure number 2, we converted 3 at an angle of 60 degrees into 1.5 plus 2.6j. So taking our two rectangular forms and adding them together, we end up with a result of 5.36 plus 3.64j. Converting back to the polar form, z is equal to the square root of 5.36 squared plus 3.64 squared, which is equal to 6.479. The angle is equal to arctan of 3.64 divided by 5.36, which is equal to 34.181 degrees. So rounding up my answers, I come up with an answer of 6.48 at an angle of plus 34.2 degrees. So now I'd like to show you how to use your calculator to solve all of these problems. So the first thing that we're going to do is press the mode button, and you can see 0 is flashing. That's for normal mode. So I'm going to use the down arrow key, and now I'm going to press 3 to select complex mode. When you're in complex mode, in the top left-hand corner, it'll either display XY for rectangular components, or it'll display R theta. So under procedure, step 1, we converted 4 at an angle of 15 degrees to 3.86 plus 1.04j. So on my calculator, to put it into rectangular mode, I press second function, and then just above the 9 key you can see the arrow XY. So if I press second function 9, that puts it into rectangular mode. So in the top left-hand corner of my calculator, you can see it says XY, and that means it's in rectangular mode. So under Procedure, Step 1, I can just type in 4, and the DMS key is how I put the angle in, so I press the DMS key, and then I press 1, 5. So on my calculator screen, you can see it's put in 4, angle, 1, 5. When I press the equal key, it gives me an answer of 3.86. Then I press the second function key and exponent. And the calculator gives me 1.04 I, which is identical to the answer that we've got under Procedure, Step number 1. So under Procedure, Step 4, we're converting to the polar form, and we have 4 plus 3j is equal to 5 at an angle of 36.9 degrees. So to convert from rectangular to polar, I'm going to press second function, and then you can see it's got an arrow, r theta, just above my 8 key, so I need to press second function 8. So now in the top left-hand corner of my screen, my calculator shows r theta. So to enter my rectangular number, I'm going to press 4 plus 3, and the I key is the A, B/C key, and then I'm going to press equal. So on my calculator screen, you can see I've got 4 plus 3i is equal to 5. And when I press second function, EXP key, it now tells me I have an angle of 36.87 degrees. And you can see under Procedure Step 4, we have an answer of 5 at an angle of 36.9 degrees. Under Procedure, Step 6, we're to perform the following calculations, and we're adding two rectangular numbers together to come up with 12 plus 4j. So to add rectangular numbers together and get a rectangular answer, we need to change our calculator to rectangular mode. So we press second function 9. And now you can see XY in my top left-hand corner. Now to add those two numbers together, I'm going to put in a bracket, 10 plus 8i, close bracket, plus bracket 2 minus 4i, close bracket, equals. So you can see the answer is 12. And then I'm going to press second function, exponent. So it's 12 plus 4i, which is the answer we've got under Procedure, Step number 6. So under Procedure, Step number 9, we've got 6 at an angle of 90 degrees times 3 at an angle of minus 44 degrees. So I need to change my calculator to the polar form, so I press second function, 8 key. So now you can see I've got an r theta in the top left-hand corner. So now I'm going to type in 6 angle 90 times 3 angle 44 minus and then I'm going to hit equals. You can see the answer is 18, and then I press second function, exp, and it's at an angle of 46 degrees, which is identical to the answer we've got under procedure step number 9. Now under procedure step number 10, we were doing the following non-right angle operation, and we had to convert to rectangular form first, and then convert back to the polar form. Our calculator can do all those steps for us at one go. So with your calculator in the polar form, and you can see I've got r theta in the top left hand corner, I'm going to type in 4 angle 15 plus 3 angle 60, and then press equal, and you can see I've got 6.48. And when I press second function, exponent, I've got 34.1 degrees, which is almost identical to what we calculated. Now our number is going to be off a bit due to rounding errors, and when you do it on the calculator, there will be no rounding errors. So under procedure, step 11, we're going to be drawing the following expression as time domain graphs. So the first one that we're given is v equals 8 sine 2 pi 100t. So 8 is going to be the maximum positive voltage. It's going to be a sine wave, and the 100 is the frequency. So the frequency ends up being 100 hertz. Now the period is equal to 1 over the frequency, so 1 over 100 hertz equals 10 milliseconds. Now I want my waveform to fill the graph as much as possible. So if I want it to go to the top of the graph, and that's going to be my 8 volts, then each division is worth 2 volts. And because I've got it set up here as 90, 180, 270, and 360 degrees, and remember that 360 degrees is one complete cycle, you can see we go over 1, 2, 3, 4, 5, 6, 7, 8 divisions. So our x-axis is going to be 10 milliseconds divided by the total number of divisions representing 360 degrees. So it's 10 milliseconds divided by 8, and that's going to equal 1.25 milliseconds. So one division over is 1.25 milliseconds. 90 degrees would be 2.5 milliseconds. Unless told otherwise, we always start at the zero crossing and continue up to our maximum, which is going to be 8 volts, and that's at 90 degrees. We go through the zero crossing at 180 degrees. We reach our maximum negative voltage, which in this case is minus 8 volts at 270 degrees. And then at 360 degrees we go back through the zero crossing point again. So under procedure, step number 12, we have a sine wave with a time delay. So looking at our formula, you can see it's v equals 8, so 8's the peak, sine 2 pi 1000, so the frequency is going to be 1 kilohertz, and it's plus 45 degrees. So remember, plus 45 means to move to the left, so it's going to be leading. So my frequency is 1 kilohertz, my period is 1 millisecond. I'm going to be using the entire graph, so I'm going to move it up 4 divisions. So 8 divided by 4 gives me 2 volts per division. So 2, 4, 6, 8 volts. On the x-axis, that's going to be 1 millisecond for the entire period, and we know that one period is going to take 8 divisions, So 1 millisecond divided by 8 is 125 microseconds. So each one of these divisions is 125 microseconds. Now we know it's going to be plus 45 degrees leading. So 2 divisions is 90 degrees on either side, so we need to push it back to the left 1 division, and that represents a starting point of 45 degrees leading. So that will be our new zero crossing point. Our peak will be 45 degrees shifted from our 90. So typically the maximum's at 90, but we've shifted it to the left 45 degrees. Same thing with the 180 degree zero crossing. It's shifted to the left by 45 degrees. Our 270 degree maximum minimum voltage is shifted by 45 degrees. And the final zero crossing, that would be at 360 degrees, is also shifted to the left by 45 degrees. Now under procedure, step number 13, we have a sine wave with a positive DC offset. So V equals 2 plus 2 sine 2 pi 100t. So 100 is the frequency. 2 is our maximum voltage, so it's going to be plus 2 minus 2, but it's raised up by 2 volts. So it's actually going to go 2 plus 2, which equals 4 volt peak, and then 2 plus 0 for our zero crossing. So our zero crossing is going to be at 2 volts, and then 2 plus minus 2 is 0, so our maximum negative voltage is actually 0 volts. So our frequency is 100 hertz. Our period is 1 over the frequency, which is 10 milliseconds. To draw this waveform, I'm going to use 1 volt per division, and the x-axis is 10 milliseconds divided by 8, which is 1.25 milliseconds. So my waveform would normally start at the 0 line for the zero crossing, but it's moved up 2 volts. And then it would continue to the 2 volt plus 2 volts, so that's 4 volts. The zero crossing at 180 degrees is shifted up 2 volts, and then the maximum negative is actually 0 volts because it's shifted up 2 volts. And then the final zero crossing at 360 degrees is also shifted up by 2 volts. Now under procedure, step 14, they want us to graph the following. 4 at an angle of 15 degrees plus 3 at an angle of 60 degrees. And you'll notice these numbers come from procedure step number 10. Now in procedure step number 1, we already converted them to the rectangular form, and we came out with the answer, but now we're going to draw it graphically. So on my graph, I've decided to go 2 divisions over and 2 divisions up to generate my zero crossing point. I've drawn in my first vector. You'll notice it's 4 at an angle of 15 degrees. Now this is a protractor which I printed off the internet to try and get in my 15 degrees. So you notice it's 10, 20, so it's halfway between 10 and 20, so that is 15 degrees. So using a protractor is a lot of work, but since we've already converted to rectangular, you can see I can go over, and each one of my squares is half. So I've gone over half 1, half 2, half 3, 3.5, 3.86 is approximately here. And then I've gone up 1.04. So that's half 1, that's approximately 0.04. And then I've drawn in my resultant, and that happens to work out to 4 at an angle of 15 degrees. Then on the head of that vector, we have to draw in 3 at an angle of 60 degrees. So rather than putting a protractor on there, I've decided to use my rectangular component, which is 1.5 and 2.6j. And then I've drawn in my resultant as 3 at an angle of 60 degrees. Then finally, I've drawn in what 4 at an angle of 15 plus 3 at an angle of 60 is equal to, and it's equal to 6.8 at an angle of 34.2 degrees. So under procedure, step 15, we're to write the time domain expression for the following descriptions. So our description is a 5-volt peak-to-peak sine wave at 100 Hertz with a -1 volt DC offset. So remember, our formula is V is equal to A max sine omega t plus our phase angle. So omega is equal to 2 pi f. So our formula becomes 2.5 because it's maximum and 5 volts peak to peak divided by 2 is 2.5. Followed by sine of 2 pi frequency, and the frequency is 100 Hertz. Now there's no phase offset to this waveform, but there is a DC offset of -1 volt, so we just put in -1. We could also write the answer as -1 plus 2.5 sine 2 pi 100. So under procedure, step number 16, we have a 10-volt RMS sine wave at 1 kilohertz lagging by 40 degrees. So remember, lagging equals move to the right, and when we move to the right, we subtract the phase angle, so we have to subtract the -40 degrees. 1 kilohertz is the frequency, so that'll be 1000. You'll notice it's given as 10 volts RMS, so we have to convert the 10 volt RMS back to the peak voltage. So remember, to go from peak to RMS, we divided by √2. So to go from RMS back to peak, we can multiply by √2. So the answer becomes 10 times √2 sine of 2 pi 1000, and it's -40 degrees. Under procedure, step number 17, we have a 20-volt peak sine wave at 10 kilohertz leading by 20 degrees with a 5-volt DC offset. So keep in mind, leading means move to the left, which is equal to plus. So we typically start with our positive 5 volts DC plus the 20-volt peak sine 2 pi 10,000 for the 10 kilohertz, and it's plus 20 degrees, meaning leading. When you've completed your lab, show it to your instructor and have them initial it to indicate that it is complete.